Today, Guillaume Remy, to talk about the exact formulas and Gaussian details and the area of the quantum disk.
Okay, so I'd first like to thank the organizers for putting together this wonderful conference and for giving me the opportunity to speak here. So today there will be two parts to my talk. The first part will be, I'm going to review some of the recent progress that has been made to prove exact formulas on the Gaussian multiplicative chaos measures using the techniques coming from Liouville conformal field theory. And in the second part of the talk, I'll present you, so it's a work in progress I'm doing with Yuan, who's here, and also with Shin-sun. And we're trying to compute, I'll probably explain this, to determine the law of the area of the quantum disk. Okay, so let me start with the first part. And so this research program that I've worked on for the most part of my PhD, so with Remy, who's here, also with Vincent Vargas and Tunan, who's here as well. So this program started out by this paper by François David, Antti, so Remy and Vincent, where they give this connection between the Liouville conformal field theory and the Gaussian multiplicative chaos measures. And then following that in a set of papers, so there's this method that was developed to prove exact formulas on Gaussian multiplicative chaos measures, so using techniques that come from from conformal field theory. Okay, so this is the take-home message of the method: is that studying the Liouville conformal field theory, you can introduce the right observables for the Gaussian multiplicative chaos measures. And there will be a solution to some differential equations known as the BPZ equations after Belavin, Polyakov, and Zalmochikov. And so you study the solution space of the equations, and then you get some non-trivial relation on the quantity you want to compute. And at the end, you have an exact formula, such as the DOZZ formula that was proved by Antti, Vincent, and Remy, and this Fyodorov-Bouchot formula, which will be the one I'll be explaining to you today. Okay. So since this is the last day of this conference, I'm not going to spend too much time on defining what is the Gaussian free field and the associated Gaussian multiplicative chaos measures, but I'll try to keep all the definitions on this board. So okay, so we're on the unit disk. Everything will, and I'm working with the Gaussian free field that has free boundary conditions or Newman boundary conditions. So this is its covariance. And this also, it's good to notice, it just reduces to 2 log x minus y if one of the points is on the boundary. For instance, x is on the circle. Okay. So then you have for any value of the parameter gamma in 0, 2, you have the area Gaussian multiplicative chaos measure and the boundary measure, okay, which you define by a limiting procedure that you all know. Okay. Okay. So now the main quantity of interest for the first part of this talk is this. It's the total mass of this Gaussian multiplicative chaos measure on the unit circle. So I have this y of gamma is, I'm integrating over the circle the boundary, the Gaussian multiplicative chaos measure on the unit circle. So this y is a random variable, it's positive, and it depends on one parameter gamma. So when you have a random variable, the most natural question you can ask is what's its law? So this is the goal of the talk, to answer this question. Okay. So there's one key fact you need to keep in mind to understand the proof is what is the condition for the existence of moments of this variable y? Well, it's that a moment p exists if p is smaller than some bound 4 over gamma squared. And here p can be any real number. It can be as negative as you want. Well, it's real, but it has to be smaller than 4 over gamma squared. Okay, so now the main result is a proof of this formula that was conjectured by Fyodorov and Bouchot. So they're working in statistical physics. So it's so the Fedorov-Bouchot formula is the computation of the moments of the random variable y. So for all values of the parameter gamma in 0, 2, and all p smaller than 4 over gamma squared, and you get this ratio of gamma functions. Okay. But now, if you're a probabilist, maybe you prefer this equivalent statement, which is just to say that y has this law, which is up to some constant. It's an exponential law of parameter 1 to the power minus gamma squared over 4. Okay. So let me just very briefly mention how Fedorov and Bouchot conjectured this formula. Is that actually it turns out you can easily compute the positive integer moments. So if you have some integer n that's smaller than 4 over gamma squared and positive, then you can write, when you compute this moment, you can write n integrals and exchange them by Fubini with the expectation value. And then you're left with the expectation of an exponential of a sum of Gaussians, and you know all the covariance. So after 2 lines of computation, you land on this integral, which is a circular variant of the famous Selberg integral. And its value is known to be this ratio of gamma functions. Okay? But now, of course, you've only proven this for a finite number of points, these n integers smaller than 4 over gamma squared. So this is not, you would like to replace n by any real p smaller than the bound. But of course, this is, well, you can't do this. You have to find a way to make this heuristic rigorous. Okay? And this is where we're going to use the ideas coming from the Liouville conformal field theory. So let me explain how this will go in this model. Is that there's this function g of t. Go right in here. Where I'm choosing, so I have my circle, the disk, and I have some point, some parameter t in 0, 1, and I introduce this auxiliary function, which is I'm adding in the Gaussian multiplicative chaos measure this fractional power. Okay, and then I still have the rest. Okay. So it might seem mysterious, why is this the right observable to study this problem? Well, it's because G is solution to some, so to a second order differential equation known as the BPZ equation. Okay. So now, to complete the proof of the theorem, there's 2 things I need to explain to you. The first thing is, well, where does this function g of t and this differential equation, where do they come from? Okay. And the second step is, well, how do you use this knowledge to complete the proof? Okay. Because it's not obvious how knowing this gives information on the moments of y. Okay. So, so for this, let me do the second step first. Let's assume that this is true, that g is a solution to this differential equation, and let's complete the proof. Okay. So this differential equation, it looks a little convoluted, but if you do a change of variable, if you go from t to t squared, then it's a hypergeometric equation, and these equations are very well understood. You could just open a book on special functions, and so the solution space are it's a real vector space of dimension 2, and the idea of the proof is to write the solution in 2 different bases. So the first basis will correspond to a power series expansion around t equals 0, and the second basis is a power series expansion around t equals 1. Okay, and so since the vector space is dimension 2, for each basis you're going to have 2 coefficients. So the blue for the first one and the red for the second one. And of course, if you're writing 2 different bases of solution, then there's a matrix that will allow you to go from one to the other. So so there's a change of basis formula that will link the coefficients that's just given by the theory of hypergeometric equations. So now I'm asking you to believe me that that you can find the values for these 4 constants by basically just performing direct asymptotic expansion on the expression of g of t. So there's one that's very easy to see, is if you take t equals 0, then the term you've added in just disappears. So you basically just, this disappears and you just land on the moment p of y. So this is the first constant, c1. But then you can do the same thing with the other constants, and what you find is that c2 is equal 0, that b1 is, so this you find this quantity, which is unknown at this point in the proof. You can't do anything with it, but you find b2, which is some ratio of gamma functions times the moment p minus 1 of y. And so now the theory of hypergeometric equations is linking you the red and the blue. So it implies, since c2 equals 0, you can write a relation between c1 and b2, and this implies this relation between the moment p of y and the moment p minus 1. Okay. And so this with this relation, you can compute recursively all the negative moments of the random variable y. Okay. And now, so you land, this is the formula that was conjectured by Fedorov and Bouchot, so it matches. And to complete the proof, now we just apply the theorem of probability that says that if you have a random variable and the series, the exponential power series associated to its moments has a finite radius of convergence, then the moments completely determine the law of your random variable. And here we can apply this to the 1 over y, since I've computed all the negative moments. And so basically, this is enough information to determine the law, and we know explicitly the law we're looking for, because it's this exponential law to some power. So, so this completes the proof. Maybe I should mention, so this was the second step, studying the solution space of the differential equation. So this was, in Liouville theory, this was first introduced by Teschner. It's called Teschner's trick. And okay, so but it's really now a recurrent method that's always used to prove these exact formulas. Okay, so now let me move on to the second, which was actually the first step of the proof, which is to understand where this g of t came from, and where do you get the differential equation from. Okay. So here, now I have to introduce what is the Liouville conformal field. Yep.
To show you back the recurrence relation.
Yes.
The recurrence. That's before. Yeah. So there'd be no way to access this last equation. There would be no way to get this directly.
I don't know of any way. Otherwise, that would be an alternative proof. But the only rigorous computation that I know of is the integer moment one. So, yes.
I mean, can you just show the definition of this one? Is there a way to understand this? I mean, the thing that you take the peak moment of here, in terms of something that has to do with the area or something that touches the boundary. You know, because you're integrating over the length of the boundary of something between the this function to this power of gamma over 2. Could it be something that has to do with the the mass of loops that touch the boundary at that point that's around the point t or something like that? So that one is integrating something that has to do with the area. I mean, so the question is it conceivable that this integral between 0 to pi could be interpreted in some geometric way by?
So I think
because if you add a CLE on top of it and all the usual.
Because at some point you need to recover the special value, right? So maybe we can write it like this: so the Gaussian free field plus gamma over 2 log t minus. So this gamma over 2, it can also be equal to 2 over gamma. These are the two special values. So I don't know if we can see this in the shifting the field. I'm wondering if this didn't disappear in the quantum zipper at some point to shift x either by gamma over 2 log or 2 over gamma log. Yeah, but
we're not going to solve it now. But just the question whether there is.
But I'm not.
I mean, that's not something that is sort of obvious.
Okay, maybe we can discuss later.
Yeah, we'll discuss it.
Okay. So here now I have this. Okay, I want to explain you a bit of the Liouville conformal field theory in the disk. So I think we've seen this non-rigorous path integral definition. You've seen it a few times in this workshop already, in Shourab's lecture or Vincent's lecture yesterday. So basically, the correlation function of the Liouville theory is you consider a product of the exponential of your field at some points zi with these weights alpha I, and the definition a physicist will use is you write this formal path integral. Okay, so you have the quantity you want to compute, and you weight. So dx is the formal measure on the space of maps, and you weight everything by exponential minus an energy, and your energy is the Liouville action. Okay. So in the Liouville action, there's the gradient squared term. So if this was the only term present, you would have just a Gaussian free field. It would be free field theory. And in Liouville theory, you have exponential interaction terms. And when you're working on a domain with boundaries such as the disk, you can choose to place the interaction either in the bulk, so integrate over the disk, or on the boundary. And each of these, you can have some free parameter in front, so the cosmological constants. One for the bulk, one for the boundary. Okay. And so, to prove this Fyodorov-Bouchot formula, we make the special choice just to set the bulk to 0 and keep only the boundary. And now, this is there's a way to give a probabilistic meaning to this path integral. And so I'm asking you to believe me that this is true, but when you do this, the 1-point function in the disk, so with the particular choice mu equals 0, is just the moment p minus 1 of y. Okay. And this 2-point function here will be up to some explicit constants or factors. It's just the function g of t. Okay. So the parameter alpha here is linked to the p. And here you see this second point, it's chosen with a special weight, so minus gamma over 2. And this is required to have the differential equation. It's linked to these two, well, there's these two special values that you have to pick. Yes?
In a way, this is the way you found the G by
yes.
using Teschner trick.
Well, no, this is not Teschner trick. This was
gamma over 2 phi.
I guess, oh yes, you insert, well this, but this is, to find that this was known, I think, before Teschner, that these observables were solution to differential equation. He just found a way to extract information from the, I guess, yeah. So,
anyway, this is the way you found it.
Yes, yes.
And where's the mu delta? Where's
Oh,
the
it's, okay, so I put it, it's just in C1 and C2, it's just some power. This one, no, it's not. I could set it to any. It doesn't matter any value. It only these parameters you'll see matter when you when they're both positive. Then there's some ratio that remains of them, but otherwise it's not important. So when you have such a correlation function, where one of the weights of the field in your correlation has a special value. That's either the minus gamma over 2 or the minus 2 over gamma, then your whole correlation function is solution to one of these BPZ differential equations. Okay. So I'm applying this technique to this 2-point function. Okay. So one with this special value minus gamma over 2, and you can write down the differential equation that's satisfied by the 2-point function. So here. I'm writing everything on the upper half plane, H. But so in all this conformal field theory business, you can map. Then you can map by conformal map. So if you have some point Zi and some point Z, then by a conformal map, I can map one of the points to 0, and then I still have the rotations left. So I can map the other point to T. And so I can make this. Apply this change of variable on my differential equation. Okay, and this will lead to the differential equation for g of t. I should also mention, so this is really a theorem of probability that you have to prove. You have to make this rigorous. You have to compute all the derivatives, and you do integration by parts on the underlying Gaussian free field measure, and at the end you find 0. So you really prove this. And also, I have to say, I didn't see this differential equation written as it is. I didn't see it in physics. Well, although there's an interpretation for it, the way you find it is there's well, you can interpret these terms with the z bar in a sense as if they're seeing a mirror image to the insertion z somewhere in z bar. Well, there's some interpretation you can give of these terms with z and the z bar. Okay, but okay, so this is the equation you need. So yeah, so this completes all the steps of the proof of this Fyodorov-Bouchot formula.
Just
Yeah.
one thing, there are works, so I don't really remember the details.
Mhm.
They were worked by Kostov and Petkova, I think, and years ago, and also Serban, where they looked at the disk, the Liouville disk with, mu on the boundary, like a mu inside, and they calculate correlation function
Yes.
of points on the boundary. You know
Yes.
this one?
Yes, I know there's conjectures for more general correlation function. Yeah.
Just end up with-
Yeah. So since I intended this to be a little bit a review of all the exact formulas, I want to mention the result of Vincent and Remy for this DOZZ formula. So it's giving you the value of the 3-point function of the Liouville theory, but this time on the Riemann sphere. So in this case on the sphere, it's the most fundamental quantity because 3 points is exactly the number of points to fix a conformal map or conformal automorphism of the sphere. And I've written here the path integral definition in this case, so with again the Liouville action. And so they proved an exact formula for this quantity using similar technique, but it's much more involved than the one I showed you today. And there'll be a talk by Tunan on a similar result we did in collaboration for the Gaussian multiplicative chaos measure on the unit interval, so you'll hear about this afternoon. Okay, so now I want to move to the second part of this talk, which will be related to the, so it will be,
Sorry,
some,
I
yeah.
don't want to slow you down, but just one question. Could you explain intuitively why, when you take exponential alpha phi of 0, so on the center, it's related to the integral of the measure on the boundary? It was not totally obvious.
Because we have a definition. So if you're working with just the mu bulk 0 and just with mu boundary, this reduces up to constant. It's a moment of the Gaussian multiplicative chaos measure. And these points you have here, they create log singularities in this way. But here it's in 0, so you get IE theta minus 0, and it's to the power gamma alpha over 2, I think. Or no. But so this gives 1. Yeah, so this. And then here there's some power that you could just call P. Well, it's actually Q minus alpha over gamma, but okay. I think I have a slide on this second part that also explains this a bit more. So now I want to talk about this work in progress I've been doing with Ewan and Shin. So we're trying to give the law for the total area of the quantum disk. So as you know, there's many different approaches that we've seen throughout these 2 weeks to study these problems of random geometry in 2 dimensions. So I've stated here, I think, the 3 main approaches. There's the one coming from the mating of trees framework of Bertrand, Scott, and Jason. There's the one you've seen in the first part of this talk. And then there's also the whole side of the combinatorics on random planar maps. And in each case, you'll see that you can give an answer to this question of what is the total area of the canonical random disk in a sense. So it will be either quantum disk in this setting or called Brownian disk. Okay, if you're working with on the planar map side. And so I hope this will be a good way to see connections between different talks we've seen throughout this workshop. And also as an output, so this is still a work in progress. This isn't a proof, but using the computation that will come from the Liouville theory side, you can give a value for the variance of this speed of the pianosphere Brownian motion, which was, I think Jason pointed out in his lectures that this was an open problem. And so you'll see, I'll try to explain how you can get this value. Okay. So let me start with the mating of trees side. So in this framework, so you're working with the equivalence classes of these quantum surfaces. You see you have a surface with a GFF type distribution on it, and everything is defined only up to conformal maps. Okay, so this is why you're working with equivalence classes. And they're both equipped with their natural so LQG measures. You have the area measure and the boundary measure. And so as we've seen, so I won't go in more detail on this because we've seen this many times in Jason's lectures and Wendelin's lectures as well, that so they're the natural objects that will come from the scaling limit of discrete models with the topology of the disk. And you can also describe them, the quantum disk, we saw this in Wendelin's lecture, is also the bubble that's cut out by an SLE kappa curve with kappa between 4 and 8. Okay, so and this will be useful to find the law of its area in the mating of trees setup. But so I want to say that throughout the rest of the talk, I will condition on the boundary length every time to be 1. And so you have some total area for the quantum disk. And again, this is a positive random variable. So the most natural question to ask is, what's the law? Okay. Yep. So let's try to answer this question. So on the mating of trees side, there's this description, as I said, that we saw in Jason's lectures, which is that there's this SLE curve that will be cutting out, so filling up one of the bubbles, it cuts out. And you can define this right and left processes. And they're basically the two components of a 2D Brownian motion. So you can take this description as a kind of, if you want, as a black box. And what you have on the Brownian motion side is a Brownian motion that does the following thing. Okay, it starts from 0, 0. You condition it to stay in the upper in this quadrant. So this is a singular conditioning, but you can make sense of it by some limiting procedure. And so it's conditioned to exit in 1, 0. So the 1 is because we're conditioning on unit boundary length. This 1 here is the length of the quantum disk. And the time t it takes to do this is the area. Okay. And so now by a computation on Brownian motion, you can give the law of t in just as a function of the parameters of the left and the right components of your Brownian motion, right, of the variance and the covariance. So in the covariance, you see this the famous cosine term that appeared in Wendelin's lectures and in Jason's lectures and many other places as well. But so what's important here is that the global constant for the variance is not known. This a squared, this speed is not known. So using this description, what we find is the law of the total area, which is so it looks like this. So up to some constants, it's this inverse gamma law, right? So it's exponential minus 1 over u and u to some power in front. And this you determine it in terms of the unknown a. Okay. So I have to mention that this is only for now proven for gamma between square root of 2 and 2, because in the other phase, so this is a work in progress to extend it by Morris and Ewan, because in this case the SLE doesn't really cut out a bubble, so I think there's more involved to recover it, but it's also it should be doable, I think. And so what I want to mention is that this now this law also appeared in all this the planar map side. So for instance, I think I was told this was not a difficult exercise to find this law. In the case gamma equals square root of 8/3, and of course there's much more in these papers than finding this law. But what's interesting to see is that by these combinatorial methods, which are so they're completely different techniques, you do land on the same type of distribution. Okay, so for gamma equals square root of 8/3, or there's a paper by Nicolas and Inchao and Pascal, who does this for the ON model, so you can link it into other values of gamma. Okay.
So,
Yeah.
is this the same calculation that gives the mating of trees constant?
No, well, this is the last part of the talk. I'm going to try to explain to you how you can recover this law from the Liouville conformal field theory point of view, and you're going to land on this law, but with no unknown constant, in a sense. So then you can match them up.
This is a mating of trees.
This is just mating of trees at this stage, yes.
And the drawing motion.
Okay.
Yeah, let me, so this is the last part of this talk. And how do you recover this
Should
law?
show this
Yeah.
slide before. Should show the slide before. The slide before. Yeah, this comes from this.
Right, okay, right. So it's the same.
To just make a comment, I mean, just for people to connect to the various people, various things that we talked about this week. I mean, you can do it with the mating of trees directly because you're cutting out discs, but I guess with the thing that I explained yesterday, Wednesday, when you explore disk and you cut it into disks, then you just knowing the fact that the area of the disk you start with is the sum of the areas of the disks that you end up with, you can get a functional relation which is exactly the same as the one Nicolas and Pascal and Mark as well. So that gives another way to get to the same thing. But of course it's in the spirit of the mating of trees, so there's nothing new
But
compared to what you're doing there.
But just to be clear, this A that you compute here is
Not completed.
Here it's just unknown. Here it's unknown, and you get so you just do a computation on the Brownian motion, so you
Right.
get the law of t as a function of a. Just this.
Going to be Liouville afterwards.
okay. So this point you're just doing it. You're not computing either one of them. You're just relating them to each other
Yes.
right now. Okay. Got it.
But
And later
it's
you'll-
still giving you the shape of the law up to unknown constant from mating of trees.
Yeah. Okay.
So now this is to relate this to the Liouville conformal field theory picture, you have to understand the equivalence of both frameworks. So there's a paper by Yuanaru, Yichao, Wang, and Shinsun on the equivalence in the case of the sphere. And there's a work in progress, so on the quantum disk to do the same thing in the case of the disk. So there's Baptiste who's here who worked on this with Jason, and also Shin was working on it independently. Okay, so this is, let me state the equivalence is that we have this relation that, so I'm characterizing the law of the area of the quantum disk by the expectation of any functional of the law, and you have this formula. So I think Vincent yesterday also wrote the similar formula in the case of the sphere. So let's try to demystify a bit this formula. So basically this first, you have f of an integral over the disk, okay. And since you're conditioning on unit boundary length, you have to divide both the area and the boundary measures by the total boundary measure. But there's a scaling that appears that means that the area measure gets, if the boundary gets divided by the total boundary length, the area gets divided by the boundary squared, okay. And when you do this conditioning procedure, there's the total mass of the boundary that appears to some power. There's one subtlety also that I don't want to discuss is the position of the marked points in all these different descriptions. But basically, since they're all gamma insertions, you can create them or remove them by the Gersonov trick or by just reweighting or sampling points according to boundary or area measures. So here I guess I put one in the middle of the disk, but so you have to do this correctly. But yeah, I don't want to get into too much of this detail. And now, so what will we be able to compute on the DKRV side? Well, there's this one-point function, okay, which has this definition. And here I'm writing a definition with both parameters positive, okay, I mean with both interaction terms. So there's both the bulk and the boundary. And with both mu and, so you have two free parameters, mu and mu boundary. And there's this conjecture that we expect to be able to prove using the same techniques that you saw in the first part of the talk, although this is still the work in progress, is that so it was conjectured by these physicists, okay? And it's just this value for the one-point function, okay? And when you do this story with mu equals 0, then this is really the Pierre-Bouchot formula that I presented in the first part of the talk. But now I'm claiming that to get this law of the quantum disk, you really have to work with both parameters positive, okay? And what will you be able to, how do you relate this to the mating of trees side? Well, it's because there's this statement of equivalence that will then you can express this this quantity that the physicists have a conjecture for. You can basically express it as this integral of this expectation of where you have the quantum disk that appears. And this one has the density that I showed as previously with the unknown constant, the unknown variance. Okay. So here there's also another subtlety that will be, well, that I don't want to discuss too much, which is, if you notice, there's this integral is diverging. Well, you have to subtract one term to make this really rigorous. So physicists, what they do when they write these formulas, they don't really worry too much about this, and there's a gamma function with a negative argument. So there's some sort of analytic continuation that takes place somewhere. But so hopefully we can write a rigorous proof of this. And for now, so for just what I'm presenting today, I just want to subtract one term so that I have so that the integral converges in 0. Yes, this is a similar type of things you do to And so I just show you that now you can you have two methods to compute this observable. You have the one that we hope to be able to prove in Liouville conformal field theory, but here I'm just taking the formula from physics as an ansatz, right? And I can compute the 1 point. And so I'm computing power series of this mu bar parameter, which is the right ratio of my two free parameters. So the boundary divided by the square root of the bulk. Okay? And on the mating of tree side, well, you do the same computation using this definition. Yeah, you could just compute this. You power expand in mu bar, and you know this law. So this is what you find. And there's the unknown constant, the mating of trees, well, the variance of the Brownian motion, right? So now since they match, well, there's only one choice, which is this value, which, okay, so I think there are sanity checks you can do to see that so it diverges, for instance, in gamma equals 2, but this is because basically the S3 curve will wind very quickly, and so it will cut out bubbles that have extremely long length and very small area. So to be able to get a very long length in a short time, you have to have a large variance for the Brownian motion. So this is, I think, heuristic explanation for why you expect a divergence here in in gamma goes to 2. And you can, I think, also do a similar explanation around when gamma goes to 0. Okay. So now I just have a few concluding slides. So why should you care about this, the value of this constant? Well, so there are these pictures we've seen throughout this workshop, especially in Jason's talk. Is that when you have this map decorated by the two spanning trees? Okay, we've seen this the Mullen bijection to encode this with the two walks, well, the two processes in red and blue. And so in the mating of trees picture, you have this. You have this convergence, right? And it's here now. On this side, the two Brownian motions, you can completely characterize them. So I guess this knowing this constant just removes an unknown constant that appears in this arrow, on this this picture. And so then if you have some functional on the discrete side, you can remove one of these unknown constants when you write a convergence. Okay. So okay, maybe a few more concluding remarks. So concerning the first part of the talk, so there's this big program of computing more exact formulas on Liouville theory. So for instance, we need to compute on the disk this 1 point to prove that was related to the second part of the talk. Okay, but you could also be interested in other geometries, proving formulas on higher genus. And there's also this big conformal bootstrap program, so understanding how, for instance, in the sphere, how the 4-point function decomposes on the 3-point function. And in this process, you're supposed to have these universal conformal blocks that appear. So this is, I think, a nice goal to try to understand this. And considering the other part, so maybe there, hopefully this will be a more, we could find more connections between the different approaches for studying random geometry. I should also mention, so the value of A that we can determine is, I think, yeah, it's very universal in the mating of trees setup, so it appears in all the different, it's the same value for all the different topologies. It gives you connection with discrete models. So I think also you can relate, there's two notions of boundary lengths. There's the one for the quantum disk and the one for the Brownian disk. And there's it's up to some constant as well. And knowing the value of this constant, then you can identify the second one as well. So I think it just makes a lot things more explicit. And this is also another question I have. Maybe it's possible to prove more exact formulas from mating of trees side in some way, because I mean this law that you get is in a sense an exact formula, right, for the area of the quantum disk. So okay, I think I'll stop here.
Are there more questions? No, let's think.
Hey, let me just add a comment and say I'm very, very happy to see that A. Because this is something that we had absolutely no idea how to get. And it's just really a remarkable story.
Well, thank you, yeah, for attention.